First of all, thanks for having me again, and it really gives me a lot of pleasure to actually talk about my research and my project. I've personally invested a lot in this project, so it started back in. It's just to give a background of what motivated me for this is basically back in February of last year, I was actually doing a course, and in that course, I was actually training some neural networks on some common problems, and I was like tweaking the parameters, like changing the learning rate, the batch size, adding regularizers, just to see how it affects my performance. And one of the things that I observed was people often talk about is to change the activation function you are using and try some other activation function out there which might be a better option for you rather than just using value. So one of the activation functions that I came across was by Google Brain, that was published in 2017 at ICML, and the paper was titled as Searching for Activation Functions, and they had proposed this new activation function called as Swish, and it's basically a very simple activation function. It's the formula is x into sigmoid of x. So that was the equation behind Swish. So I was really fascinated because Swish really improved the performance of the neural network architectures by a lot as compared to ReLU or LeakyReLU. And I wanted to know more why Swish was this good, or why Swish was so robust in the results. So I found out some properties of Swish that were very favorable in any given activation function. And that's where I started to try to come up with a new activation function which had those properties, but actually improved the performance. So one of those properties was, unlike ReLU, which actually thresholds the negative side to 0, so no negative information is preserved. Swish does preserve a bit of the negative information, which is important going up in the propagation of information throughout the neural network architecture. A bit of the negative information actually drives more better generalization from the network. Another property was Swish was not piecewise linear like ReLU is. So Swish is continuous. It has a continuous differentiable derivative, and that is really helpful in the path propagation and also the gradient calculation. So one of the key problems of ReLU, which is the tying ReLU problem, is because ReLU thresholds the negative side. It was clarified by Swish. So those are two important properties of Swish that really help push the accuracy even higher as compared to ReLU. So with that in mind, I actually designed 5 different functions which closely resemble the graph of Swish, and one of them is right now known as Mish. So in this graph over here, the red line, as you can see, is Mish, while the light blue start line is Swish. So they are very close to each other with a very minute difference. Mish is defined as x into tan h of soft plus of x. This inherits one of the very important properties of Swish, which is called as self-gating. So that's a very common property in LSTM networks. So according to the Google Brain authors who wrote the paper for Swish, they term self-gating as the property in activation function, where the input is multiplied with a input modulated by a nonlinear function. So in case of Swish, it was input multiplied with sigmoid of input, while in case of Mish, it is input multiplied with tan hypotenuse of soft plus of input, where soft plus stands for logarithmic of 1 plus exponential of input. So that's how Mish came into existence. And after that, my task was just to benchmark it to prove its validation and how robust it is as compared to other activation functions. So some of the properties of Mish which really makes it favorable is that it is continuously differentiable for infinite order, so it doesn't face any gradient based problems whatsoever. It is non-monotonic, so and the derivative also is non-monotonic. This actually helps in better information propagation through the network. One of the favorable properties is approximation of identity near origin, which means that if the activation function is defined as f of x, so the property states that for any given activation function as f of x, f of 0 should be equals to 0 and f dash of 0 should be equal to 1. So the original function at 0 should be 0, while the first derivative of the function at 0 should be 1. So both Mish and Swish did satisfy the first property. Both of them are located at origin in the f of x curve, while for the f dash of x curve, they are half of identity. So that's a favorable property that both Mesh and Swish have. The range of Mesh is somewhat close to minus 0.31 and it extends to infinity. So it is unbounded in the positive side, just like Relu and Swish are. It is unsaturated, unlike tan hypotenuse or sigmoid. And as I said, it is unbounded in the positive domain. So this particular graph is of general importance to understand why Mish tends to perform better than ReLU especially. So this graph is very simple. It means that we initialized a random neural network, and then once we have initialized it, we pass scalar values of the coordinates of these of this graph. So if you can imagine that this graph is basically pixels, so this have x and y coordinates. So we pass those x and y coordinates to the network, and we obtain the scalar magnitude at that point in this graph. So this is what output landscape means. So as you can see for ReLU, the gradient transition is very sharp. You have
Sorry?
yeah, go ahead.
I do not understand what are these graphs. What is the network used to get them?
Okay, so it's a 5-layered randomly initialized feed-forward
Okay.
network.
Okay, but after it's still random when you generate the graph. You keep the weights random.
Yeah, it's completely random. So
Okay.
what we do is if we I guess I can draw over this. Yeah. So just imagine. Yeah. So for this graph, if we can just imagine each block to be 1 pixel. So
Yes.
we pass the coordinates of those blocks to the neural network, and it gives us the magnitude for that block. So this is 0, 0, 0, 1, 0, 2, 0, 3, 0, 4.
Okay.
And similarly, we pass all these coordinates to the network, and the network will generate the magnitude, the scalar magnitude for that region. Or you can say the pixel intensity for that region.
Okay, thank you.
So you take one single network with random parameters, or you take several different networks randomly initialized average or something like that? Or it is one single instance?
It's just a single network. It's just one 5-layered randomly initialized network.
Okay.
And I have another question on the properties. You told at first. You told us the importance of identity approximation. Is it due to the fact that you tend to regularize at initialization and with regularization layers afterward, but you need to have these kind of properties and there are kind of what you like general cool properties for activation function? Where does it come from, basically?
So the more important reason why we have approximation of identity in your origin is because of f of 0 being 0. So you want for any given null input which is having no real value or no real weight, the activation should always result to give you 0 in the activated nonlinear output. So that is the more important property in terms of approximation of identity near origin. But to be honest, we still don't know why the activation function desirable property should have approximation of identity near origin, which I will discuss up ahead. It is a desirable property for the f of 0 equals to 0 part. For the f dash of 0 equals to 1, most of the activation functions which doesn't even satisfy that regime still works pretty fine. So it is more important that the activation function at 0 should be having the activated output as 0 itself. So that is the more important prospect in terms of approximation of identity origin. This is more discussed well in a blog post that I have linked to at the end in the reference, so I'll share that for the clarity.
Okay, thanks.
Yeah, so also the thing is that if we know that we have seen if activation functions do satisfy the property, neural networks tend to learn better when the weights are initialized with very small values. So it has been empirically observed that an activation function having that property helps. So since we know that weights tend to be initialized near 0 with small standard deviation, so the more crucial region for an activation function is the part closer to 0. So outliers don't play much role in terms of how the function curve looks like.
Okay. So, wait. So, for example, it will be an issue if you, for example, add values and you go forward than 0. For example, you kind of normalize to 1.
Sorry, I couldn't get it. Can you come back on that?
So, Mish as it is would be less effective if the mean values of your weights would be around 1, for example.
So usually our weight initializers are clustered to 0, so we don't expect that. So that question actually is more connected to a domain called as mean field theory. So in mean field theory, basically what we do is we have our weight initialization. So for the weight initialization, we take the standard deviation for both the weight and the bias, and for any given nonlinear activation function that we are using in the network, we actually can divide the gradient process or the importance of weight initialization into two different phases. One of the phase is called as chaotic phase, and one of the phases is called as ordered phase. So the graph looks something, I can actually show that graph to be honest. So let me open up that graph directly. So okay, that would be okay. So I guess this is visible.
Yeah.
Okay, so here basically the x-axis is the variance of your weight matrix, and this is for the bias matrix, and you are dividing your where your network will initialize into two phases. So one is ordered phase, one is chaotic phase. So if you're and this Q star line is basically called as edge of chaos or ordered chaos transition. And to obtain this Q star line, you have to define the activation function. So it is dependent on the derivative of the activation function. So if your network falls on this line, which is called as Q star, then your gradients will propagate fine. There won't be any issue. But if you fall in any of these two phases, for example, if you fall in this ordered phase, you will face the issue of vanishing gradients. And if you fall on this phase, which is chaotic phase, you will face the issue of exploding gradients. In case of ReLU, because it is not continuously differentiable, this Q star line actually decomposes to a single point, and that point is at 0, root over 2. So the bias matrix needs to have a variance of 0, while your the standard deviation of your weight matrix needs to be at root over 2 to make sure that your ReLU network doesn't face vanishing gradient or exploding gradient. So the real advantage that Mish comes into play at that point of time is that the Q star line for Mish is continuous and doesn't decompose to a single point as it does in ReLU. So this is a complete different domain of understanding activation function. So if you want, you should go through this paper. Is really intuitive of understanding how activation functions and weight initialization actually plays a role in network convergence. So this topic is mostly related to dynamical isometry, which means that if your network reaches dynamical isometry, which is nothing but your input-output Jacobian spectrum reaching identity or becoming equal to 1, your network will converge faster. So that is dependent on your activation function and your weight initialization process. So that's where the derivative of an activation function plays more importance than in conventional benchmarking. So this is definitely an important resource if you're looking forward to go in depth into that domain more.
Okay, thank you.
Okay, so sorry. Okay. So just to compare where Mish stands and what ReLU offers, because ReLU has been used as the standard so far in most of the neural network architectures. So ReLU converts all the negative input to 0, while Mish does preserve some small negative weights, which proves to be important. Mish has the order of continuity of infinity, so it is continuously differentiable, while ReLU is not continuous. Because of that reason, Mish doesn't cause dying gradient, while ReLU causes the famous dying ReLU problem or the dying gradient problem. Mish generates smoother output landscape as compared to ReLU, which was seen over here. So just to clarify on this graph means that if the gradients here or the transition you see from the blue shade to the red shade is more smoother, it means your loss landscape will be smoother, and thus you will easily optimize and generalize better. So as you can see, the transition for ReLU is much more sharp as compared to that of both Mish and Swish. So that is an important point in terms of why Mish helps in many ways. Also, Mish ensures better information propagation when the number of layers increases in the architecture. So you can say that for larger architectures or more complex architectures, Mish is a better choice to go for as compared to ReLU. And ReLU is piecewise linear and monotonic on both quadrants. But the pro point for ReLU, which is a benefit of using ReLU, that it is less computationally expensive as compared to Mish. So there is a trade-off between better accuracy and faster inference.
How much longer exactly does it compare?
So it depends on network architectures. Like various networks have different comparisons, but recently we were able to actually use CUDA optimization to optimize the function for Mish and make it nearly 8 times faster than it was originally. So now it is very comparable to that of ReLU. So on a single forward pass, ReLU uses on a standard MX resonant network around 167 millisecond, while Mish uses around 210 milliseconds. So it's a difference of 50 milliseconds per forward pass. So it's very comparable. Earlier it was around 800 milliseconds, so now we were able to reduce it. And we are still optimizing it further to even decrease the cost. In terms of CPU level, so we use JIT decorator, and also we use certain optimization. So instead of using the conventional tanh, we actually converted it to its exponential form. So we optimized the CPU performance around 11 times better than it was earlier. So we are still working on it. The only issue we are facing right now that the optimized versions for Mesh aren't still performing really good on double precision data points. So they're performing really well on single precision data points. And since double precision isn't used a lot, so it's not a major concern, but we are still looking to optimize it further, and we are making progress with it. So if we can make it around in the region of plus 20 milliseconds, then Mish can be as competitive as ReLU is.
Okay, thanks.
Okay, so these are one of the two tests that I did which really sheds more light into why Mish is more robust as compared to both ReLU and Swish. So this is a very simple experiment. What we do is just use a network and keep on linearly increasing the number of layers on that network and see how the test accuracy decreases. So as you can see, until 15 layers, the test accuracy was maintained around 98 to 99%. This is just on MNIST. After 15 layers, ReLU started to drop significantly, and you can see the drop was pretty fast. So from 98.8%, it decreased to around 22.3%. While Swish also did decrease from 98.9 to around 38%. While Mish didn't decrease that much, it still retains an accuracy of around 83.5% after increasing 10 more layers from the base 15 layers that we had observed at the start. So this proves that Mish is actually more robust in case of the network architecture being more complex or the number of layers becoming increasingly more in large models. There is an actual proof on ImageNet, which I'll show in the later slides. But this was a very simple test to prove the same, that Mish is more robust and more capable in terms of handling higher number of layers in the network.
And what's the difference, the main difference between Mish and Swish that like come up with those results? Because I understand really the continuity and stuff like that would prevent better testing accuracies, but for Swish, what happens? What's the difference between Mish and Swish that prevents it from failing after 23, 25 layers?
That is something that we still haven't figured out yet, because Swish actually doesn't have good thresholds, we believe. In case of soft plus operation that we use in Mish, which have thresholds that we define so that we make our activation functions results better, Swish doesn't enable those thresholds to prevent gradient overflow or gradient underflow. So because of that issue, we believe that Swish performs bad in cases of higher number of layers. Also, you'll see up ahead that Swish is not suitable for certain architectures that we have proved by testing it on ImageNet. Also, one of the tests that I used in my experiments, where I tested activations against different optimizers. In case of Adam W, Swish actually drops from around 85 to 11% of accuracy, while Mish stays at 83. So I think there is a link between optimization processes and activation function. We're still working on it to understand, because right now the main focus for us like for me when I'm working on Mish is the mean field theory, which will help us to understand more about how Mish performance is related to weight initialization and the optimization process. So after those experiments, I think we'll have better answers to the question that you have. Also, we are working with someone whose name is Javier IDME. I don't know if you guys know him, but he is the creator of lostlandscape.com. You guys can search it up online. It's a very famous research project that he had done, where he visualizes the lost landscapes of network architectures.
I got it in my best
So,
of AI, by the way. Yeah.
yeah, so we are working with him to actually generate the lost landscape to compare how the lost landscape looks like for Mesh as compared to Swish, so we can get more clear, definitive answers of why Mesh is tad bit better than Swish. Because right now, both the output landscapes as shown over here looks pretty similar. So, and also the shape of the activation of Swish and Mesh are pretty similar as are their gradients. So we still are not clear why Mesh push the accuracy better as compared to that of Swish, but we'll have the answers to that in the coming weeks up ahead.
Okay.
Okay, so one more thing that we did is that we tested how different weight initialization processes affect the test accuracy for both Swish and Mesh. And as you can see here, we tested basically all available weight initialization processes on PyTorch, and we saw that Mish consistently has a higher accuracy as compared to that of Swish. So also in our tests, which isn't shown over here, it's on the paper, Mish is actually more robust to input Gaussian noise. So with increasing input Gaussian noise, the decrease in test accuracy is less for Mish as compared to that of Swish and ReLU. So that proves that Mish is more robust to input Gaussian noise that your input data might have. So that's a better option to carry as compared to Swish and ReLU. Okay. So far as compared in terms of benchmarks, we have benchmarked around 40 activation functions in 80 tasks, ranging from image classification on CFAR 10, CFAR 100, ImageNet, to NLP-based tasks like sentence classification, sequence tagging, named entity recognition, to segmentation models like ENet on Cityscape dataset, UNet, and efficient nets on Stanford CARS dataset. So far, Mish has outperformed ReLU and Swish in terms of 75 total tasks. It has outperformed them 55 and 53 times respectively. This is one of the examples where we used a squeeze excite ResNet on CFAR 10 dataset using Adam Optimizer. So you can see that Mish has the highest test accuracy and the lowest test loss. Also, since someone had asked earlier about how slow Mish is, so this is the non-optimized version of Mish that you're seeing over here. It's faster than GELU, which is another very famous activation function used in GPT-2 and BERT algorithms. So it's considerably faster than that. It's very close to eSwish and Swish, but so this is not the optimized version. So using the optimized version, it is faster than even Swish is concerned. So this is one of the examples that we have in the paper. But in the repository, we have plotted for every single benchmark that we have done for every single network architecture. So you can definitely go through the repository to know about all the results and all the benchmarks that we have available. Okay, so this is the thing that I wanted to point out. So this is a ResNext 50 model, a very common architecture used in a lot of domains. So here what we did is we basically combined some other state-of-the-art algorithms which can boost performance along with Mish. So this one, which doesn't use Mish, is the default architecture, which is using leaky ReLU. So for leaky ReLU, the default accuracy is 77.9%. So then we just tried using some different tools or processes that can improve our accuracy. So we used mix-up, we used cut mix, we used mosaic, we used max blur, we used label smoothing. Some of them did improve the accuracy, some of them didn't. And then we tried out Swish. In case of Swish, the accuracy actually dropped from 77.9 to 64.5%. So that is around 13% decrease in top one accuracy. While simply swapping the leaky ReLU with Mish, we actually increased the accuracy with plus 1%. Then we combined all of those state-of-the-art algorithms that we use, cut mix, mosaic, label smoothing with leaky ReLU, and we got 78.3. But when we added Mish activation, we got another 1.3% increase on ImageNet. So this is a very, very interesting observation that Swish actually decreases in accuracy considerably by 13%, while Mish actually improves the accuracy by 1.3% on leaky ReLU with state-of-the-art and 1% on just swapping leaky ReLU. So this is one of the very crucial observations that we found out of why Mish is robust to many different architectures as compared to Swish. Additionally, on our repository, we have made available 4 different networks along with their weights. So you can use it as pre-trained networks in your models. Those are ResNet 50, ResNext 50, DenseNet 201, and DarkNet 53. So all 4 of these networks are available on my repository. You can download and use them as a pre-trained model. As of right now, Mish is available on more than 30 official packages, starting from TensorFlow to DarkNet, FastAI, Hugging Face Transformers, OpenCV, Allen NLP, DLib, and many more. We are still awaiting to get added to PyTorch. Hopefully we will, but for using Mish in PyTorch, it is very simple to define a custom activation function. So it's very easy to swap the activation like ReLU with, as compared to Mish. So some notable achievements that Mish has received so far is that recently on the Stanford Dawn benchmark, which is the official benchmark that Stanford maintains for different data sets in terms of costs for training a neural network and how fast they train. A ResNet 9 with Mish actually holds the world record on fastest training of CIFAR 10 on 4 GPUs. It also demonstrated the property of Mish, which is it converges faster. So it reduced the number of epochs required to 14 from 18, which was earlier using CELU activation. Additionally, MX ResNet using Mish, Max Blur, and Ranger Optimizer actually holds 12 official records on FastAI leaderboards for ImageNet and ImageWolf classification, which are actually a subset of the original ImageNet dataset. Also, I had the fortune of actually having my paper and my repository trend for 3 days on paperswithcode.com, and it was also trending on GitHub, and was also featured on 2 very important blog posts which covered the most interesting AI papers of the 3rd quarter in 2019, and also covered in the Decade of Deep Learning article, which was shared by many. So these are some of the references that I believe are very influential to understand what is the intuition behind Mish and how it came into existence and why it is better. So I'll share this presentation with everyone so that you can go through these links and find additional information that I might not have been able to present during the presentation. Okay, so that's it from me. If there is any question, I would love to answer them.
I have a question on the last one. You say that it achieves some results on fast training, but before we explained that it was easier to handle, faster to handle ReLU, even if you improved it. So is it only because you have less epoch for your training, or is there something else?
So here's the thing, ReLU is faster per epoch, so which means ReLU might take, let's say 20 seconds per epoch, while Mish might take 28 or 30 seconds per epoch. But to reach 94% accuracy, ReLU might take 30 epochs, while Mish will take 20 epochs. So Mish actually takes less number of epochs as compared to ReLU to reach convergence. So if we are able to optimize Mish even further and reduce the epoch timing or the computational complexity that Mish has, then we can essentially say that it's a better option than ReLU. So that's the comparison benchmark between how fast ReLU is and how fast Mish is.
Do you see any more areas of improvement, or you think Mish is already pretty much perfect, or is it only in terms of optimization, or just in terms of the function itself? What are your future plans? Do you plan on work more on developing other activation functions, or maybe improving on this one? What are your plans?
I'm glad you asked that question. In fact, I'm actually developing a new activation function right now. It's much better than Mish so far. In fact, I can share one of the very important observations that I have found out with those two activation functions. So let me share my screen once again. Okay, give me 1 minute over here. Okay, so I showed this experiment which showed that the decrease in test accuracy as compared to the increase in layers, right? So as you can see, ReLU again drops pretty fast, Swish drops again pretty fast, Mish stays at around 85. But these are the two new variants that I've designed, which didn't even drop considerably until 27 layers. So they are actually even much better as compared to Mish, and they're actually faster than Mish, much faster than Mish, in fact. Unfortunately, I can't share the function as of right now because it's still under development. So this is just a sneak preview into what I'm working on currently. The cool thing about these two new activation functions is that they do not follow the property of Mish, which is self-gating. So they are not having the formula where the input is multiplied with the nonlinear function of the input. They actually follow another formula. So based on that, I believe that it is really important to actually push the boundary for activation function, because so far, based on the review or feedback I've received from many people, the major concern is that Mish is slower than ReLU. And there is always this concern, whether people want higher accuracy or whether people want faster training. So to address that issue, I have been working on Sharkfin, and I hope that if I can consistently prove that it is providing better results as compared to that of Mish, then it can replace Mish and also hopefully ReLU as a standard activation function up ahead. So those are my future plans for Mish. And also for Mish, my future plan is to optimize it even further and reduce the computational cost so that it becomes a more viable option for researchers, especially because as academicians, we want to prove we want to push our state-of-the-art accuracy and improve our current models. So that's my future plans for Mesh. So definitely it's not the perfect activation, but it's a very strong competitor as compared to Relu and Swish.
Any other questions?
Yeah, I have another one. If I'm not mistaken, you said at some point that on some tasks, I think it was something like 1/3, Relu was actually better than Mish. So do you see a pattern in the tasks on which it's better and the tasks on which it performs worse?
So far, my testing has been extensively on image classification and image segmentation. I didn't have the opportunity to actually benchmark natural language processing tasks as much as possible. So I'm still doing that. But so far in my experiments, I've seen that in NLP-based tasks, TANH and Relu are actually more strong competitors as compared to both Mish and Swish. But again, I'm not in a position to actually say that they are the best because I haven't done that many experiments in NLP. So I have to do much more benchmarking and experiments in NLP-based tasks to actually find whether they are whether Mish is actually better than Relu and TANH, or whether Relu and TANH are actually the best option. So the tasks where actually Relu and TANH are actually a bit superior to Mish is in some of the NLP-based tasks. But so far in image-based tasks, like image classification, image segmentation, object detection, Mish has been by far consistently better than both Relu and Swish.
Okay.
Okay, so thank you very much again for joining us today. It has been extremely instructive and interesting, and thank you for the great presentation. And is there anything, are there any questions you want to ask Sicara? Maybe, I don't know, because I just feel that we're so obliged now.
I mean,
yeah.
First of all, I really appreciate you guys inviting me over, and it was really great to chat with you guys and especially answer your question, and also present my work. After all, whatever I'm doing, be it Mish or any other work that I'm involved in, is again for the community and for people like you who are researching on cutting edge AI-based technologies, and for you guys to try and provide me feedback. So it has been really immersive experience for me. I would really love to know what you guys are working on. I would love to see your work, and I would love to go through them and maybe provide my feedback. I mean, I'm still pretty much newcomer to this field as compared to experts like you. So, but I would definitely love to read or try out any of your guys' work if you have it online and open source. So I'd love to give that a try. So yeah, feel free to pass me any links or any papers if you guys have online, and I'll definitely give that a read. And I hope that I can also have some questions, not stupid enough, which I can ask you, and know more about your work. It's as always, it's a constant learning experience. So thanks again for having me.
Thank you.
Thank you. Okay, so we're definitely gonna stay in touch, and I think we shall try and implement try maybe using Mish on some of our projects, and we'll get back to you with the results. And yeah, we'll also please keep us updated about the new activation functions you're working on, because we're all really hyped. Okay, thank you so much.
Bye.
Thanks.
Yeah.
Thank you.
Thanks.
Have a
Bye-bye.
nice day.
Bye.
Bye.
Oh, c'était cool.
Cool.
Ouais.
Alors, c'est quoi, hein?
C'est rien.
Je suis pas sûre que ça a marché pour l'enregistrement.
Ah non.
J'ai pas du
Pas grave, moi j'ai vu
tout,
PH, il a pris plein de notes.
Il y a 10 minutes.
pas du tout l'impression que ça marchait.
Je pense que le
Mais
bruit est
bon.
dans l'article.